Hello, today we're going to be learning the Bellman-ford algorithm. So what is the Bellman-ford algorithm? It is a shortest path algorithm for graphs. So we're going to start with an S node, so our S node here, and the S node is always going to have a shortest path of 0 because it takes 0 nodes to get to S. And every other node is going to start with a shortest path of infinity. And over time, we're going to fill these out to newer and newer shortest paths. So what we're going to do to solve this is that we're going to ask the nodes in a sequential order. So we're going to go from S to A to B to C to D and to E. And we're going to ask this question. For all outgoing edges, so if we're looking at S, for all outgoing edges, is there a new shortest path to that destination node? So at the beginning, E and A here are going to have infinity, and we're going to find 8 and 10 for these nodes. These will be the new shortest paths for these nodes. And the idea is that when we ask the same question to the nodes over and over again, new paths will be discovered. So at the moment, A seems to have a path of 10. But the moment we discover path D, so when we go from S to E to D, when we discover this, we're also going to discover this -4 path, which will be the new shortest path for A. To do this, what we're going to trace out is 2 tables. We're going to trace out 2 tables. So the 2 tables are going to be our iteration table, which is going to keep track of these shortest paths. And then we're going to have a parent table to figure out what came from what and what leads to where. So let's go ahead and start tracing this. So let's start tracing this. We see that our setup here is going to be 0 through infinity because our starting node is always going to be 0, and everything else is infinity because we haven't reached it yet. And then for our parents table, everything is going to be null, and for S, we're going to see a recurring pattern of S always being null because it is the starting node, so it isn't going to have a parent. Now, we're going to start with our first iteration. Our first iteration, we're going to bring down the 0, and we're going to start with S, and S is going to look out, and we're going to see this 8 and 10. So the new shortest paths to A and E here, A and E, we're going to have 10, and then we're going to have 8. And now those are all the outgoing edges from S, so we'll move on and examine A. Examining A, we see a new path leading to C using this 2 path over here. So we're going to add 2 to its existing path, so 2 plus 10, and that is less than infinity. So we're going to add that to C's new shortest path, so that's going to be 12. Then there's nothing else to examine from A. We're going to look at B, but we're going to see that B is infinity here, so we can't really examine that, so we haven't reached that yet, so we're going to skip it. Then we're going to look at C, so we can examine C, it has a number. And then C has this new path leading to B here, so -2 plus 12, that's going to be 10. So that's going to be B's new shortest path. And then there's nothing else to examine from C. We can't examine D because it's infinity. We can examine E here, so we can examine this E. And we're going to see this new path to D is found. So we're going to do 8 plus 1, so that's going to be 9. And let's examine the parents that we have here. We're going to see that S is still going to be null, and then we got A from S, we got B from C, and C from A, and D from E, and E from S. So let's go ahead and start the new iteration. I'm going to bring down this 0. We're not going to really see anything new from this S. We can just move on. We can move on, and we're going to look at A here. A doesn't really provide anything new. We can look at B. B does give us a new path, 1 plus 10, but that's larger than A's shortest current path, so we're not going to add that because that's going to be 11, which is not going to give us anything meaningful. So we can move on. We can look at C. Again, nothing meaningful. But when we get to D here, we do have something new, that we have this -4 path leading to A. So -4 plus its current, so -4 plus 9, that's going to be 5, which is shorter than 10. So we're going to put 5 down here. We can see this new path also, so this -1 down here, this -1 leading to C, so -1 plus 9, that's going to be 8. So C is going to have a new shortest path of 8 as well. So put 8 down here, and then that's all we can examine from D. So we're going to move on. We can examine E, and from E there's nothing really new, so we're going to lock in these numbers. So we're going to have 10, 9, and 8 brought down, and we can look at our third iteration. We're going to look at A. We're just going to skip S because there's nothing new that's going to be added here, but in our code it's still going to be examined. But looking at our A here, we're going to see that, okay, leaving A now, we can re-examine this 2 down here, so we're going to re-examine this 2. So 2 plus 5 is going to be 7, which is shorter for C. So C gets this new 7 here, and then we can move on to examine B. B is not going to have anything new here, and we can look at C. C is going to have this new path. Its new path is 7, so 7 plus negative 2, that's going to be 5. So B is going to have 5 now. We can move on, we can look at D. D is not going to offer anything new, so we can just move on. E also not going to offer anything new, so we can move on. So let's bring down what we have. So 5, 9, and 8. Now let's start filling in this parent table. We've been neglecting it a little bit here. So again, this was null, and this A here, so A, this 5, this A, that came from our D, so let's fix that. That came from our D. B here, B didn't get anything new. It's still C, so we're going to bring that down. C here, still A, so we're going to bring that down. For D, it's still E, and then for E, it is still S. Now, when we brought it down again, on this third iteration, that A is still going to have D, and B is going to have C still, and then C is going to be A still, and then D is going to be E still. E is still going to be S. Now we're going to run this one more time. We're looking at this, and we see that S is still the same. Looking at A, there's nothing really we can improve on because there's no new path leading to A. There's no new path leading to A, so it's still going to be 5. B here, we did get something new, so 5. That's going to be 5 plus 1, that's 6, but that's larger than what we already have, so we're not going to add it. We're going to bring that back down. C, we still have that 7. We're still going to keep what we have. We're still going to keep what we have. We have D, and D here. D gets nothing new, so it's still going to be 9. It's still going to be 8. We see that there's no reason to keep iterating. There's no reason to keep iterating because there's no new paths we have found, so there's no new parents, so there's no reason to keep iterating because we're going to keep getting the same thing. So we can exit early with Bellman-ford if there's no new paths found, because if there's no new paths found, well, there's nothing new to evaluate. So there's no new shortest path that could be evaluated. And this is how you trace Bellman-ford. There is one thing that the Bellman-ford algorithm cannot handle, and there are negative cycles. A negative cycle is a cycle whose total weight is negative. So let's look at some examples below. We're going to find a path from A to C that is the shortest. So we'll start with A, and then we'll go to C. We'll see that we'll take this 5 path here, and then this negative 2, which is going to lead up to 3. But if we keep going around, we're going to have 2, then plus 5 again, that's going to be 7, so we're not going to achieve anything better there. So the best we can achieve is this 3. We can move on. If we move on, we can go, okay, we can have this 5 here. We have this negative 7. That's going to be negative 2. But we're stopped by this incoming, so we can only really end up here. So that's fine. And then when we go to this 3, we'll start with A. We'll go to this negative 7. So this 5 and this negative 7, that's going to be negative 2. But we'll go out to this negative 1. We'll get negative 3. And then we'll do negative 3 plus 5, that's just going to be 2. Then we'll do this 2 plus this negative 7, but that's going to be negative 5. And if we keep going again, we'll have this negative 6, and then we'll have this 1 here, or this negative 1. And we'll go again, and then we'll get negative 8. And we can keep going around and around in a circle, and we'll never end. This is something that's really bad for the Bellman-ford algorithm, but we do have a trick up our sleeve to stop this. So we can actually solve this. Let's recall why we stopped early. It's because we asked every single node, hey, do you have a new shortest path? and they said no, then there's no reason to keep iterating, because there's no new path we could possibly find to find a new shortest path. Well, then this begs the question, what is the worst case on the amount of iterations we go down? Say we have n nodes. So we have n nodes here, so S, A, B, C, D, and E, and we're going to exclude S because we start with S. We already know that path. Then for every iteration, the worst case is one node reveals a new path. That means at least every iteration, there's one new path. So the maximum number of those that we could possibly have is n minus 1. So if we go past n minus 1 iterations, we know we have found a negative cycle. And that's how we detect negative cycles, and what is the maximum number we actually have to iterate, and our break early case. If we just don't find any new paths, we can just break early. So what is the runtime of the Bellman-Ford algorithm? We know we're going to have at most n minus 1 iterations. We can get rid of that 1 because of the constant factor. Well, what do we do every iteration? Well, we go to each node, so each n node, and we ask it, what are your outgoing edges? This is the same as trying to traverse the entire graph every iteration. So if we had a hash table of our graph, so if we had our n entries here, and we had S, A, B, C, D, and E, S entries are going to be A and E, A entries are going to be, what do we have here? We have C, B is going to be A, and so on. We can call these entries here M, and we know that we're going to traverse all of these entries, and we know we're going to traverse all of these entries. We're just going to go one row at a time. So this means that every iteration, we're going to do n plus m. So that's going to turn out to n squared plus nm. Well, we already are accounting for this n here, so what's the largest out of these two? Since we're doing a plus, we just want, is this one larger or is this one larger? But it turns out that n squared isn't larger, and m is, because m could be less than or equal to n squared. This means a full adjacency matrix. So this means that if all of these entries here, so if all of these entries on the right of m were full, this would mean n times n, where every node is connected to every other node. This is a full adjacency. So in reality, the worst case could be n cubed. It could be n cubed, but since m is variable, we're just going to keep it as m. Because in practice, usually most of the time, m is not going to be n squared, but since m is a variable that we really just want to keep track of, it's going to be big O of m. And that is the runtime of the Bellman-Ford algorithm. And that is the end of the video. If you enjoyed it, don't forget to like and subscribe. If you are looking for the code implementation of Bellman-Ford, it is linked in the description below, along with an open source algorithm textbook open for anybody to contribute to. And with that, thank you.